Solve applications involving exponential equations. We're going to look at half-life examples. And the half-life is the time it takes for half of an unstable material in a particular sample to decay. And so what this means is it's really the time that it takes half of the what are called parent isotopes to decay to their daughter, the next generation isotopes. And for carbon, which is one that uses biology to be dating with, the half-life is 5,117 years. So what we do is we use an exponential equation, and the exponential equation we use is sitting right here. It's a of t, which is the amount after time t. So I'll just write amount after time t is equal to a sub 0, and that's my initial amount. And then we have e to the kt. T, as you would guess, would be what it would be?
Would it be time?
Be time, good. And then k is your exponential growth constant. Now, when I take a look at carbon, its half-life is 5,715 years. That means half of those isotopes will decay in that amount of time. So what I want to do is see if I can come up with a value for k knowing this. And the way I'm going to do that is just simply rewrite my equation. I'm going to rewrite it here in blue. I have a of t is equal to, and then I'm just going to have a0 e to the kt, and I'm going to go ahead and think about half-life. Half-life means once t, which would be 5715, is put into the equation, half of the original amount is gone. So how much of the original amount would then be there?
Half?
Half, sure. And so that would be 0.5 times the original amount. So I'll make that substitution. So now I have 0.5 a sub 0 is equal to a sub 0 e to the kt. Now, what I want to do is see if I can solve for k. And I'm going to do this just in terms of a general time for any substance, and then later I'll put in my 5,715 years. Now, to solve for k, what I want to do is isolate the term with e to the kt, so I'll divide both sides of the equation by a sub 0, because I really don't know that initial amount, but it's irrelevant in this context. And we get 0.5 is equal to what? Is equal to?
E to the kt.
Beautiful. I'm trying to solve for k, so I'm going to go ahead and see if I can remove its position in the exponent. And I'll do that by taking the natural log of both sides. So that would give me the natural log of what? Natural log of?
Of 0.5.
Is equal to the natural log of?
Of e to the kt.
Very good. And I did that for one very specific reason. And the very specific reason I did that is because then with the rules of logarithms, I can take my kt and bring it out in front. So I would have the natural log of 0.5 is equal to, would be equal to what? It would be equal to?
ln of e to the kt.
Sounds good. And the reason I took the natural log is so I could bring that exponent out front.
So would it be kt times the natural log of e?
Very good. I know what the natural log of e is. The natural log of e is?
That is 1.
Is 1. So we're really there. If I go ahead and just divide both sides of the equation, I'm trying to solve for k. If I divide both sides of the equation by
t,
I'll have k. So it looks like k is going to be the natural log of 0.5 over t.
Right.
And so this is the value of k for our half-life examples. All I got to do is figure out what the half-life of a substance is, put it in for t, and I'll have the k. And for carbon, I know the half-life. Carbon is what? Carbon is?
Carbon is 5,715.
Very good. So now my equation gets rewritten. My equation gets rewritten so that's very specific. It's a of t is equal to a sub 0 e to the natural log of 0.5 all over t, which is?
5,715.
Very good. And then times?
Times t?
T for time. So if I go ahead and put in any time, I can go ahead and figure out how much of that material is there if I knew, say, the initial amount. If we're using carbon-14, that is.
Right.
Well, the question we have is, how long will it take for 20% of a 500-gram sample of carbon-14 to decay? Finally get to the question. So we say to ourselves, okay, carbon-14, so we're going to use our exponential equation that we just developed. It's sitting right here. And I want to identify a few things. I'd like you to help me identify a few things. What is this 500-gram sample?
Would that be A sub 0?
Is that A sub 0? That sounds great. What are we looking for?
The time?
How long? We're looking for time. Okay. So I'm going to write that in, and I'm going to go ahead and say there's a question mark that goes right here. And then we know something about A of t, right? We want to know how long it will take for 20% of this 500-gram sample to decay.
Right.
Now, I got to think about this. This A of t is the amount in the sample after so much time has gone by.
Mm-hmm.
So I got to morph those words a little bit. If 20% of the 100% has decayed, what percent is still there?
Would that be 80?
80%. Very good. So it would be 80% of the 500 if 20% has decayed. So I'll just go ahead and write a reminder that this means 80% remains. Now I have enough information to solve t, so I'm just going to substitute in and do that. So I'm going to go ahead and write 0.8 times 500 is equal to 500 times e to the natural log of 0.5. What is it over? Over what? Over
5,715.
Very good. Times what? Times
T.
t. And do I know what t is?
Not yet.
Not yet. That's what I'm trying to find. I had a funny little curious sentence earlier, which is that the original amount didn't really matter. Do you see why? My first step, I want to try to isolate the term with e raised to an exponent. My first step is to divide by
the 500?
By the 500. I didn't even need that information, as it turned out, huh? If I divide both sides by the 500, now I have a much shorter equation to deal with, which is 0.8 is equal to e to the natural log of 0.5 all over 5,715 times t. And we know this. How do you get t out of the exponent? What do you do to both sides of the equation?
You take the natural log of either side?
Very good. So I'll have the natural log of 0.8 is equal to the natural log of e to the, now it's becoming routine, 0.5 over 5,715t. And we do that for one reason, because we want to take our exponent and
Bring it to the front.
bring it to the front. So if I do that, I have the natural log of 0.8 is equal to the, what, natural log of
0.5 over 5,715 times t.
Very good.
Times 1.
Times 1, I like that, because the natural log of e is
1.
1. So we're basically done. All we have to do to find t is divide by its coefficient, which means we're basically just inverting and multiplying.
Absolutely.
So t is, I'm going to come over here, t is what? T is equal to natural log of 8, or 0.8, excuse me, multiplied by 5,715 all over the natural log of 0.5, just what we thought when we first looked at it, probably. So enter that into your calculator and tell me to the nearest year what that would be. And if you're entering it into your calculator, just to be clear, you would enter the natural log of 0.8. You would multiply by 5,715, and then you would divide by the natural log of 0.5. That's what these students are presumably doing. So what'd you get again?
I got 1,839.82.
Very, very good. So to the nearest year, I guess that would be what? That would be 1,840
40.
40 years. Very good. Thank you.